Hi, in this video, we'll be looking at what XGBoost model is, that class of models that it belongs to, and also we'll go through a working example as to how the mathematical operations happen in the backend while using XGBoost for a regression problem. You can see a table here. This is a sample data set that we'll be using and going over the mathematical processes that are involved in the regression problem. So let's get into it. There are multiple ways in which the models are built. Now each model has its own weaknesses, has its own strengths in order to contribute to the accuracy of the predictions that we are making. We have logistic regression, which is used for classification. We have naive bayes, which is used again for classification. But some of the trade-offs can affect the performance of the models while working on different data sets. Now, naive bayes might be better in some data sets, while logistic regressions might be, giving good results in other data sets. So it is a procedure. Ensembles is basically a procedure where we combine both different sets of models that are there in this example, naive bayes and logistic regression, in order to come up with a better model which can perform together so that the accuracy is better compared to the accuracy as observed by individual models. Now extending this concept to the XGBoost model, now in our case a regression problem, what happens is multiple decision trees are built. Sorry, multiple decision trees are built, and each decision tree will learn from the mistakes of the previous decision tree that came before it. Now, this type of problem is called boosting in ensemble techniques. Now, there are different ways in which we can enforce ensemble techniques. There are multiple things like bagging, in which random forest comes. There's stacking, there is blending, and all of those things. But for the sake of this video, or for the scope of this video, we are going to stick to boosting, in which we are going to go deeper into XGBoost. Now, what happens in boosting? Like we mentioned before, all of these decision trees that are getting built have to follow two concepts or two conditions. They are called diversity and acceptability. Now, what is diversity? When we are trying to build a model using the boosting technique, we'll have to ensure that we'll be considering majority of the nonces that are there in the data set. Now, how do we do it? There are multiple ways in which we can ensure that diversity is maintained. One way is to have different hyperparameters for different models or different decision trees that we're building. We can have different models itself, like naive bayes or logistic regressions working together, naive bayes and logistic regression working together in order to give a better result when compared to individual models. You can have different data sets or different chunks of data sets that each model is seeing. And you can have different features as well in the models that you're using. Different features as in different variables going into the different models. Or you can have all of these together in a particular set of models that you're building. But boosting emphasizes that you use different data sets as well, and it also uses different features and also different models. Now, what happens is it is sort of a holistic collection of all of this. Let's see how that will happen. And again, in boosting, there are other concepts that are involved. But before we go into that, let's see what acceptability is. Acceptability ensures that whatever model that you're building is somewhat better than a randomized model that that can be built, better than any random predictions. So we are making sure that any model that is getting built or any decision trees that is getting built in the XGBoost is having an accuracy of greater than 0.5. So in these two conditions have to be satisfied for any tree to be qualified as something that can be incorporated in the boosting algorithm and in XGBoost, to contribute to the overall predictions that the model is making. Let me clear all of this now so that we can go ahead. This is about XGBoost. Now, each of these decision trees that we see are called weak learners. Now, the overall idea is that the process starts with a weak learner where the accuracy is very less, and the learnings or whatever predictions are made or whatever errors are made are passed on to the next model. So the intelligence is getting cascaded down in the process to the subsequent models that are getting built. So it is a sequential process. If we can bring in a little bit of random forest concepts here just to make some distinction. Random forest does not have this connection. It is different models that are getting built individually, which are agnostic to all the other decision trees that are there in the group of decision trees that are getting built. Now, this does not possess the information of this, or this model does not possess the information of this. So there is no communication that is happening between the models per se. Oops. So let me just clear this off again. Now there are three different models in boosting as well, which can be considered. One is ADA boost, another is gradient boosting, and the third one is XGBoost, the one that we are interested in now. Now, all of these follow the same, ideology that we just discussed, having learnings passed over to different models, but they have their own unique characteristics in which this communication happens between the models. Now, in ADA Boost, the errors that are happened that are getting made in the previous model are getting more prominence in the second model, and the second model will try to emphasize on those errors specifically and then try to correct them, while as gradient boosting and XGBoost is somewhat focusing on predicting the errors itself instead of correcting the errors, and the accuracy gets better and better when the residuals or the errors that are made are getting decreased over the models. So let's start with the working examples. Having this knowledge, let's look at the same data set that we were seeing earlier in Excel so that we'll be able to apply the formulas and calculate the numbers more easily. Now, there are multiple things that are there in the mathematical calculations as well that we'll talk about as we go through this example. Okay, let's start. Now, what happens in XGBoost is there is, like we mentioned before, the calculations or the predictions are happening on the errors that are getting calculated. Now, what I mean by this is the first step that we are going to enter in this calculation is with an initial prediction of y. Now, what happens is there's a standard value. Now, if we plot a graph, we'll be having different data points. So what XGBoost starts with is a constant value. And after that, it is going to calculate the errors that we are having from this constant value. Now, the constant value that it considers in all the standard value that is getting into the model is zero point 0.5. All of the records that are there in the data set for which we'll have to predict will be zero point 0.5. So from this zero point 0.5, we are going to calculate what is the offset or what is the error residual that we are getting from each data point. Now, as you can see, we have an error of 24.5, which is huge. Now, we are going to see how these values are going to get reduced in the subsequent calculations that we are doing so that we come much closer to these values. Of course, we are only going to see directionally how it is going to improve, but when we are actually building the model, there will be multiple repetitions of the same steps that we are going to see now. Let me just clear this off. Okay, so what happens is once we have the residuals, this will form our root node. Now, what by root node I mean is that this is the starting point. Now you have 24.5, 31.5, 44.5, and 63.5. Now from here on, it is the splitting that we'll have to do based on the decision trees that we are going to have. Now, how we do this split is something that we need to understand. Now, what happens is in the core concept of decision trees, what we are arriving at is to maintain the homogeneity or the entropy. In the previous videos that we saw, we have spoken about gene index in terms of classification, but in regression models as well, or regression use cases of decision trees, we have in classical decision trees we'll be using OLS methods, but in this case we'll be using something called a similarity score. Now, similarity score tells us what is the closeness or how much uniform the values are inside a particular node. And the formula for this is sum of residuals whole square divided by number of residuals plus a lambda. Now this lambda is called a regularization parameter. What it does is as we increase the lambda score, the overall value will come down. The overall similarity score will come down. And ultimately, how we want to have the split is that we need to make sure that the similarity score of this root node and the intermediate or leaf nodes that we are seeing, the difference between the similarity score from here to here should be the highest. Let's see how it is happening in the example below. Now, I have a couple of I have three constraints that we are considering. One is taking x2. Oh my god. Taking x2 into consideration, any data point having a value greater than 9 will belong to one node. As you can see, we have only one value here, which is 63. Applying the same 63.5, applying the same formula, we'll get 4032 and we'll get 3366.75 considering everything which is less than 0.9, less than 9. Similarly, for all the other data points, similarly for all the data points that are there in X2, I've applied the same condition and I've calculated the three splits accordingly. E2 to E3, anything greater than 8, E2 in the left node when we are considering, and right node. Now, the overall similarity score that we are seeing for this is 6724. Now, what is the criterion that we are going to consider is, like I mentioned, the similarity score difference between this and these two nodes should be the highest. So the formula is sim score. I'll mention it as SS. SS of left node plus SS of right node, uh, right node minus SS of root node. Now considering the max of this value is what we are going to consider as the best split. As you can see here, these two values are close, greater than 9 and greater than 8. But since this is having the highest value, this is the split that we are going to consider. Anything greater than 8. Just is this. So our values will be, the best split that we are going to get will be 24.3, 31.5, 44.5, comma 63.5. Now I just remove everything. So the first predicted value will be an average, right? So when we have two groups here, 24.5, 31.5, the values that will go here will be average of whatever is there in that node. It's 28, average of these two will be 54. So now that we have predicted residual, using this we are going to create, or we are going to find out what is the actual y1 or the calculated y1. One other thing that we need to have in consideration is another parameter like lambda that we saw while calculating similarity score. Now let's consider this as gamma. Both of this, if you observe it carefully, both of these serve as regularization parameters. Now you have the similarity score, whatever formula that we calculated. Let's consider this. Let's consider this as SSD. This is diff. Right. So SS diff minus gamma should be greater than 0. What this means is that whatever similarity score that we are going to get should always be greater than the gamma value. This ensures that we are having good amount of splits in the whatever decision trees that we are going to build for prediction. It will ensure certain amount of threshold is always compared with, so that the quality of splits we are getting will be beneficial. Now if you're putting 600 as gamma, this won't even be considered for calculating this. So this is one other feature that XGBoost is having. Remove all of this again. Yeah, now everything is sorted out. So let's start with predicted results. Now what we are going to do, we have seen the two regularization parameters, lambda and and gamma and lambda. Now we are going to actually see how the predictions are made. Predicted, or let's rather call it calculated y1 would be better. So how we make the calculations for y1 is that is the old value plus I guess let's call it LR into the residual. Our LR basically is our learning rate. It controls the degree to which we'll be able to make the predictions. If higher the learning rate, then higher the predictions that are made. Let's see an example so that it will be clear in our heads. Now the old value or the initial y is 0.5 and our predicted result is 28. So what will happen is our predicted y1 will be 0.5. Let's take learning rate as zero point 0.1 for now. It will be 28. So it is 0.5 plus 2.8, which is equal to 3.3, right? So this will become 3.3. Now extending the same concept, I'll be applying a formula here instead of writing everything down. And 5 plus uh, let's do one thing. Let's put learning rate here as 0.1. Here I'll be applying the same formula. 5 plus learning rate into fix this L2 into residual 1. Okay, I think I might have got it wrong. 0.5 into into F, it's 3.3. Yes, 5.9. Our new residuals will be residual 2 will be y1 minus calculated y1 is 21.7, 58.1. You can compare these two numbers. I mean, you can see, but just uh, looking at how the values are getting calculated, it's 24.5 and 21.7. So as this process continues, we'll be able to reduce the residuals and arrive closer and closer to the value that we are seeing in y. So this is the overall video about how the mathematical calculation is happening. Before we conclude, let me just change the value of learning rate. So we'll be able to see how the predictions are happening. As you can see, we have gone from 21.5 to 10.5, which is much closer to what y is. But if I increase the learning rate to say 2, it's changing drastically. We are again heading back in the wrong directions. So we should be able to identify a proper balance between the parameters that we're having for gamma, lambda, and the learning rate, so that we'll be able to come up with a better model. But the best practice is to give small numbers for all of this and let the model run its course in how many ever learners that you're going to build in XGBoost, and try to arrive at the correct number or closer to the correct values or the ground truth values that are there in our data set. So thank you for watching. If you have any questions, please put it down in the comment section.